So now that we've done all the prep work for our destruction sim, we've fractured the area of interest, created the colliders for the creature, and also a nice collider for the terrain as well. Now we can finally set up this RBD bullet simulation. So we're in this destruction geometry object section here, and we have our colliders in here, but let's also merge in our fracture. So drop in that object merge, and point this to object slash fracturing and out fracture. And when we cached out the fracture, we did an RBD pack on it so that it puts the high-res fracture in one packed container, constraints into another packed container, and proxies into a third. So to get at this data after that RBD pack, we need to do an RBD unpack. This gives us our fracture output and constraints output and proxy output here. And you'll notice that a lot of the nodes that you use to set up these bullet simulations will use these three inputs and outputs, and this allows us to very cleanly pass through all of those three different types of data, and some of the nodes may rely on more than one bit of data. So if we display our RBD unpack here and drop in an RBD exploded view, we can connect our fracture constraints and proxies to that, and then display the exploded view and turn up the scale a bit. And at first, this doesn't look much different than the standard exploded view would, but if you turn on this show constraints option, and perhaps scale this up a bit more to make it a bit more obvious, and this looks a little bit chaotic with this example, but this view can help you to see how these RBDs are constrained to each other. And for our purposes now, we don't have to worry too much about where these constraints are anchored on these RBD pieces. But for some cases like vehicle destruction, it can be helpful to, instead of having the constraint points lie in the center of these RBD pieces, you may want those constraint points to be on the edges of these RBDs. If we go into wireframe mode here, you can see that it's the centers of these objects that are currently connected to each other. And we have tools like RBD convert constraints that allow you to change the constraint types so that you can do things like have the nearby RBD objects constrained to each other at the contact point instead. And this can be quite helpful when you're doing interesting deformable RBD effects. You kind of want decent hinge points for cases like that. So in those situations, this 3 input and output thing can be very helpful. In our case, it's a little bit less complicated than that. Like I said, we don't have to worry quite as much about where those constraints are attaching to the RBDs and that sort of thing. For now, we can just use the RBD constraint properties SOP to specify how these constraints behave. And for now, I'm just going to leave all the defaults on this RBD constraint properties here. The default constraint behavior is glue, which means that 2 RBD pieces are either stuck together or they're not. There's no sort of stretching of the constraint or flexing or anything. They're completely glued together as one object until some impulse makes that constraint break, and then they're totally separate from each other. And we do have other constraint types available, and we'll start talking more about these constraint properties when we start running this RBD sim, but this is kind of similar to the RBD configure SOP in that it's mostly just a fancy way of setting attributes. So after adding this RBD configure, after our constraint properties here, I'm going to go ahead and drop some nulls on those 3 outputs just so that we can more easily see what's happening to each of those at each stage of this process here. So that first output is going to be our high-res fracture. I'll just call this render geometry. And we don't want to simulate this directly. I'll just pull this off to the side over here. The second output is going to be for our constraints. So if you display that, you can see these are all of the constraint lines that were generated during the fracture process. And you don't necessarily have to use constraint lines that were generated during a fracture process. You could certainly build your own constraint lines if you want by using the Connect Adjacent Pieces SOP. This will find nearby pieces next to each other within a certain search radius, and you can use this adjacent pieces from surface points option to get RBDs to be constrained to each other at the contact point instead of their center. But I'm not going to bother with this because the constraints that we got from our fracture process are actually quite good. And then the actual pieces that we're going to be adding to the simulation are the proxies. So I'll drop in a null for those. Call that proxies, and that's going to be the third output from our RBD configure. Maybe my organization looks a little bit weird, but you'll probably see why I organize it this way in a moment. But as I was saying, the RBD constraint properties and RBD configure are really both just setting attributes on each of these things. So going to this RBD configure SOP, we saw this before with our collider objects that we're just using these parameters to set some attributes on the points of those geometries. So in this case, we'll set the active attribute equal to 1 so that these are actively simulated. And if we look at the proxies, you can see that the RBD configure is setting point attributes on these pieces of geometry. However, in the case of constraints, the important attributes are being added to the primitives here. So one way that I like to explain it, as I've mentioned in a previous video, is that rigid bodies are sort of like fancy particles with a nice collision shape, which is why all of the relevant simulation attributes go on points, because they're sort of like fancy particles. Whereas for these constraints, the points at either end of a line are only going to describe which rigid body objects those constraint lines are connecting. So the names on the points of these lines are going to be important, but since we're describing a relationship between two pieces, the important attributes that control the behavior of these constraints are going to go on those primitive lines themselves. And that's what you see when you middle mouse on the constraints here. You can see all of these attributes that are set by the RBD constraint properties SOP. Those are all set on these primitives here. And as I mentioned with the collider attributes, if you want to, you can use wrangles to set some of these properties if you prefer, or if you need to do something really special. But otherwise, setting it via these tools is quite convenient. And these tools also give us some pretty cool extra capabilities. You'll notice that the RBD configure has this fourth input here, and if we select that node, then you can see that some of these parameters have this use bounds option. And that's what this fourth input is here. This allows us to add some bounding geometry, and this will set these attribute values within that bounds. So in the case of this area of interest, we want most of this to be actively simulated RBD objects, but we want the pieces around the edges here to be passive static colliders instead. And this is a very common way to set up any sort of a destroyed surface. For example, if you had a destroyed wall on a building and you wanted the bottom portion to stay stuck to the ground, you might just set the bottom fracture pieces to have an active attribute of 0 so that they don't move anywhere, but they still act as passive collision objects. So that's what we're going to do around the edges of this fractured area here. And we can use our area of interest that we set up at the fracturing stage, and we can use that to define which areas are actually going to be actively simulated. So let's drop in this object merge, point that to our fracturing setup, and then point that to the area of interest, which is that noisy sphere. And as I mentioned, I don't want all of these pieces to be actively simulated. I want to leave the outside passive, so I'm going to shrink this down a bit, and you could just transform this down with a simple scale, or another way that could potentially be a bit nicer is if we convert this to a VDB volume. So drop in this VDB from polygons. And this will create an SDF for that noisy sphere. And now we can erode this a bit with a VDB reshape SDF. switch the operation to erode. Let's template display that. And then increase the amount of erosion until we get a nice little passive section around the edges of our fracture here. This looks pretty good to me. We don't need a very large section around the edge to be passive. We just need enough of a passive section around the outside that it'll hold this whole fractured region in place until it gets hit. So with that bounding area defined, let's connect that VDB to that fourth input of our RBD configure, turn on this use bounds option, and now let's check the active attribute on our proxies. So I'll drop in a blast stop, connect that to this proxies null here, display that, and we'll set the group to @active equals 1. And active is a point attribute, so flip the group type to points. And now you can see this is deleting out all of the active simulated pieces. These remaining pieces have an active attribute of 0, so these pieces will hold that entire fractured region in place and allow the insides to break apart. So now let's set up the actual simulation. So I will drop in the RBD bullet solver. And the first input is the simulation geometry. So I'll connect that to the proxies. Second input is for constraint geometry. So I'll connect that to constraints. Third input is for proxies. And because I'm just passing in the proxies to that first input for direct simulation, we don't really have to worry about this explicit proxy input. The fourth input is for collision geometry. So we can either attach our colliders in there, or you can also merge your colliders in with your proxies in the first input. Either technique works fine. And this last input is for guided sims, which we don't need to worry about in this case. So let's start by just merging in our colliders. So I'll drop in this merge stop after the proxies. Let's connect the collider ground to that and grab the collider creature as well. And if you don't want to stretch these wires across your scene, you could just do object merges for those two different colliders there and object merge them in just before the merge. That might be a little bit tidier and some people prefer that. And now looking at the RBD bullet solver, we can start by picking a good start frame. So let's take a look at where the creature starts to come into contact with our RBD pieces here. So let's template display the creature colliders and then step back on our timeline here. It looks like the creature starts to contact these pieces at frame 18, so I'm going to start the simulation one frame earlier. With destruction sims like this, I pretty much always try to figure out exactly when I need to start simulating. It's kind of a waste to simulate all the frames leading up to the impact, so you can save yourself a bit of computation time by setting the start frame accordingly. And then under the solver tab here, the time scale can affect the physics of the sim to make it a bit more slow motion or fast motion. The substeps will be the number of substeps that the bullet solver uses internally for its computations. If you need more fidelity in your sim, you may want to turn that up, but I've found that the default is totally fine for most simulations like this. You can increase the accuracy of your constraints and collision handling by increasing constraint iterations here. And that's one of those non-obvious things about bullet solver settings. Some of these settings related to collisions are actually called constraint settings by the bullet solver. So constraint settings don't always mean explicitly your glue constraints, soft constraints, etc. This stuff does also affect collision handling, but we can just leave this at the default. We don't really need to mess with that. And now under the bullet object tab, the emit RBDs option allows you to continuously add more rigid body objects to the sim on every frame, and this can be useful in cases like debris simulation. This overwrite attributes option allows you to animate attributes at the SOPs level before the sim and have those changes picked up in your simulation. Now by default, all of the attributes that you've set up on your RBDs here will just be read at the start frame of the sim. So if you animate these things, they won't necessarily have the new values picked up as the simulation is running. If you want new values to be picked up by these things, then those changing attributes need to be added to the list here. For this simulation, we're not animating any of these attributes over time, so we could just completely turn off this overwrite attributes option, but it doesn't really make a difference either way. The collision padding I'm not going to mess with. This default value is usually fine. The linear and angular threshold values control the sleeping behavior. So when you have RBD pieces that are moving very slowly, you might want the solver to just stop those and stop computing their motion, which can speed up the simulation quite a bit once some objects are being put to rest like that, and they will still be used for collisions, they just won't be actively moving anymore. So if you need to tweak how easy it is for those rigid body objects to be put to rest, you can tweak that. And we don't need to mess with the density or rotational stiffness or friction at this point, but I do almost always set low bounce values initially. An overly bouncy sim is one of those things that can quickly make a rigid body sim look terrible. So I always default to a very low bounce to start. For collisions, we're not actually using this because we're just adding our colliders in with our proxies and adding that to the first input here. But if you were to add those objects to the collision input of the solver, then that behavior would be controlled here. This is defaulting to treating them as convex hulls, and we've set the animated and deforming and active versus static attributes already via RBD configure, but when you've added in collider objects without setting those attributes, you can set that behavior here. But we don't need to worry about that, since we're just adding those colliders in the first input. Under the ground tab, you can add in a default ground plane. Once again, not necessary in our case. Under the forces tab, we can adjust the gravity in our scene. And for now, I'm going to leave this at default. You can also add in some drag, and our rigid body objects will try to achieve the velocity specified here. And this can have the effect of slowing down falling objects, which in my opinion is usually not desirable. So if you start to turn up the drag because you want to calm down some of your objects that are moving quickly, you want them to slow down more aggressively, then you might not necessarily want them to fall slower as well. So one thing I like to do is to right-click the gravity and copy that parameter and paste that relative reference into the wind velocity here under the drag. So this means as the RBD pieces are slowing down, they won't slow down the rate of falling. That will still try to match this gravity value here. That might not be physically correct, but this is just something that I like to use that I find easier to work with. On the Constraints tab, we have some parameters to further affect some of those standard constraint properties that we're already setting. For this, I'm going to leave these all at default, but let's say you had a whole bunch of different constraints with different strengths that are being merged into your simulation, and you want all of those strengths scaled up or down. You can change this modifier here at the solver level to globally affect all of those glue constraints. We're not going to mess around with it in this case. And if you look at the breaking thresholds tab, this is a control that we're going to use for this sim. At the moment, we're just using glue constraints as our input, but after our initial setup, I am going to convert some of those glue constraints to soft constraints when they break, and soft constraints will not break due to collisions under any circumstances. With soft and hard constraints, these are actually fairly similar constraints, even though it sounds like their names are opposite from each other. But these are both stretchy constraints that try to enforce a distance between the RBD objects, and it tries to enforce an angle between them as well. And it will always try to achieve this relationship. It will never break that relationship due to collisions and impacts like the glue constraints will break. So this is why we have to always set some sort of breaking rules for those constraints if we ever want those soft constraints to detach from each other. By default, it has a distance threshold of 1 activated here, so if the constraint stretches out by at least 1 unit beyond its rest length, then that will be considered to have stretched too far and it'll break that constraint, and I'll just leave that default for now. Moving on to the Impacts tab, this allows us to enable impact data, which gives you a lot of extra information about all the collisions that are happening in the simulation, and it generates little points to represent all of these collision impacts that are happening. And this can be useful for some more advanced workflows. And for what we're doing here, we don't need to mess around with impact data at all, so we can ignore that for now. Similarly, we're not doing a guided simulation. On the Advanced tab, we have this control over bullet world scale here. So if you remember, we originally scaled down our overall scene to 0.3 just to put everything within a more reasonable numerical range. And if you want some control over the scale in which it's simulating, then you can play around with the world scale here. We won't need to mess around with it in this case, but it's an option that is available. Under the DOP network here, this cache memory defines how much memory can be used to store the currently running simulation. So if this isn't set high enough, as this gets to the later frames in the sim, it needs to erase the earlier frames of the sim from memory, which isn't necessarily a problem, but if you want to scrub back through it in your timeline, then it can be a bit annoying if it's cleaning up too many of those earlier frames. So feel free to increase the cache memory if you want so that it can store more of those timeline simulation frames. If you open up the bullet solver here, it has some controls for the sleeping time, which I mentioned the sleeping a little bit earlier, and if the movement of your rigid body object falls below these thresholds that you can define here for a certain amount of time, as defined here, then that's the condition under which it's put to sleep and stops moving and stops having its motion calculated. Some of these other advanced parameters we don't really need to worry about here. I don't really find myself messing with this constraint solver option at all. The only thing I really find myself ever messing with here is occasionally I will change the error reduction parameter. For standard destruction sims like this, I don't find myself needing to mess with this stuff much, but particularly for some cases like vehicle simulations, I've gotten better results by cranking this error reduction parameter up quite a bit to like 0.5 or 0.8 or so. And under the constraint force mixing options, this can make the constraint system a bit sort of spongier or softer if you increase that, which for a standard destruction sim is probably not a super useful option. I've used that one before, but not very frequently. And finally, these split impulse options here keep RBD objects from exploding apart from each other when their collision shapes penetrate each other a bit. And because our collision shapes are imperfect here, we're going to get a fair amount of collision between these convex hulls, a fair amount of penetration between those shapes, but the bullet solver actually does a very good job at not making these pieces explode apart from each other. It generally handles this fairly elegantly, and it sort of ignores that penetration until they come apart from each other, and then it will accurately respect those collision shapes. So I've been quite impressed that the bullet solver can handle this imperfect, initially penetrating starting point. And finally, under output, we have some more control over what simulation attributes are transferred onto our output points and geometry. But our default attributes should be just fine. And under the Visualize tab, we have some more controls over what simulation data and shapes and such are being visualized in the viewport. And now that we've done this quick blitz through these various bullet solver parameters, let's see what our simulation looks like. And currently I have simulation disabled with this little brain icon on the bottom of the UI here. So you can use that to enable or disable overall simulation in your scene. So with that re-enabled, let's back up our camera to a decent view here, display this RBD bullet solver, and run a flipbook. Now when you run the initial versions of your sim, you don't need to run the entire frame range. I've run this up to frame 83, and this is already looking pretty cool. However, it does look a bit slow motion to me. It almost looks like it's underwater. It's so slow. I want these pieces to fall quite a bit faster, and I don't want them to expand so far. I'd like to keep this destruction a little bit more contained closer to the area of interest. So we can certainly tone that down a bit. And also, this breakup behavior is a little bit more simplistic than it would be if we added some soft constraints in here to enforce some bending. So you can see that all of these little pieces are entirely breaking apart. We aren't really seeing any sort of flexing from pieces being stuck together. And anytime you can add that sort of detail to a destruction sim, it can really make things look quite a bit nicer. Also, we're not currently doing any speed limiting, and in this case, I'm not seeing any pieces that are really flying off too quickly, but it is often a good idea to put some sort of speed and spin limits on your pieces, because some of them can get some slightly glitchy impulses and be thrown far too quickly and far too far away from our main simulation area. It's not uncommon for some pieces to just shoot off like crazy. So we want to avoid that. So let's take a look at some of the things we can do to finesse this sim.